discussed about the forces, one way of classification is contact forces and another one is non-contact forces. The electrical forces comes in this category: gravitation, force between charges, force between magnets. All these forces are non-contact forces. Non-contact forces means you have an object here, say a mass here, another mass here, and this is attracted towards it. Same way we have done in charges also. Plus charge and minus charge, this minus charge is attracted towards it, this plus is attracted from a distance, even when they are not in contact. Initially, when these discoveries were made about the gravitation, about the charges, about the magnets and about these forces, it was very difficult to digest the concept that force can act even from a distance. So a new concept was basically introduced to explain the force which acts between two bodies from a certain distance. Field means, whenever we talk about the term field, field means a region, a space. So actually the region around a mass is called its gravitational field. The region around a charge, it's called electric field. The region around a magnet is called the magnetic field. That is the meaning of field. So the region around a charge, that is called electrostatic field. The region around the magnet, it is called the magnetic field. And the region around a mass, it is called the gravitational field. And it is supposed that mass brings about certain changes around it, and when we put another mass into this region, this mass senses those changes and experiences a force. Same happens with the charge. Every charge creates some alteration, some changes in its surroundings, and if we keep another charge nearby, this charge responds to those changes. So that is how we can explain the force on this charge or this mass. So the region around a mass, the region around a charge, some changes are created by the system of charges or by the masses, and then another mass or another charge respond basically to these changes. So this is how we have introduced the concept of electric field or the gravitational field. Take another example now. Water waves. This is the very common example that we have used to explain waves. If I drop a stone, what happens? Ripples are formed like this, and these ripples move forward. So suppose I have dropped one stone here and another one stone is kept here, or maybe cork, anything. It is dropped here, the ripples are formed and these ripples move forward. This is how the water waves actually are generated, and water carries these waves are moving onward. It means there is a transfer of energy only, not the water itself. And this cork after some time starts responding to this. So this here vibrates exactly in the same way. The vibrations are produced here. So water, it carries the water waves. Its simple meaning is this. So if I make an arrangement that there is a cork, there is a stone, it is continuously moving up. So these waves are produced, and all these particles, they experience force because of these water waves. It's very easy to explain it here. Now just imagine that if I make some system in which the charges are also moving like this. It's a point A, and I somehow make this motion of charge moving up and down. For example, I may take a comb. This example we have done in the last topic, that if I take a comb, bring it near paper pieces, These paper pieces are attracted towards this comb if this comb has been rubbed from here. This is charged. Okay. Now if this comb, I move it quickly like this or like this, then there will be a time lag. It means these paper pieces will not respond instantly, and this will be observed clearly if I increase the distance. Suppose there is a charge here and I am moving it like this, or any charged body, and there is another charged body B kept at a very large distance from it. Then this will experience force because of it. But if the distance is large, there will always be a time lag. So this will not respond instantly. And now if there is a system that it moves up and down, or I make a system where I can switch on and off. Switch on, there is charge. Switch off, there is no charge. So now if I switch on at any moment and then I switch off, so there is a positive charge, and this will experience force after some time. When this is experiencing force, maybe now this positive charge is not there, I have switched it off, but this is experiencing force now. Listen again carefully. I switch on and switch off. Positive charge comes and goes. That's it. This charge will experience force because there was positive charge, but there will be a time lag, and maybe when this is experiencing force, that charge is no longer there. So what is happening here? Actually, this charge produces a wave, we call it electromagnetic wave, and this move forward, and this particle experiences force because of that electromagnetic wave. So even when this is not here, there is an electromagnetic wave. Electromagnetic wave means there is energy, there is momentum. So this space is supporting an electromagnetic wave. This is the electromagnetic field. Just as a water wave moves in water, similarly electromagnetic wave is moving in the electromagnetic field. So this region can be called electromagnetic field, and this has its own dynamics. It has some energy, it has some momentum, and it's very easy to understand when we consider charges, accelerating charges, and the distances involved are very large. So I can say that this charge produces electromagnetic wave and this charge responds to that electromagnetic wave. So the region around a charged particle is its electric field. The region around a magnet is its magnetic field. And how will we see that? What is the strength of this field? How much force this particle will experience will tell us. Now let me do it for a point charge. Electric field due to a point charge. So there is a plus charge here and I have a point A here. This is the electric field. I am not worried about the source. There is electric field. It means there will be a force if I keep another charged particle. Let me keep a charged particle, say Q naught, and I will call it a test charge, because this charge is being used to test whether there is an electric field or not. So this will experience force. If I take it towards this point, this will experience more and more force. So this is what we mean by intensity. Intensity of electric field is determined by the force that charged particle will experience. If the force is more, it means the field is more intense. So at point A, what is the force experienced by this point, by this charge Q naught? It is 1 upon 4 pi epsilon naught Q naught upon R square if this distance is R. If I change this, I put some another charge. So this force may be, this is of Q naught. If I keep another charge, say Q1, 1 upon 4 pi epsilon naught Q1 upon R square, Newton. So this force is different. But the electric field at this point should not depend on this charge. because electric field is of this charge. So if there is no Q0 here, there is no Q1 here, then this part is decided by only this and the distance. That is called the electric field intensity. So electric field due to a point charge is actually the force experienced by unit charge. Force experienced by unit charge. So it is 1 upon 4 pi epsilon naught Q naught by R square divided by Q naught. So electric field is just 1 upon 4 pi epsilon naught Q by R square. Magnitude only. I am coming to direction also, right? So this is just the magnitude part. So the electric field intensity due to a point charge Q at distance R is 1 upon 4 pi epsilon naught Q by R square. This charge is called test charge and we take it positive. This is just to test that there is electric field or not, and this is the source charge. So this is producing a field and this Q naught is responding to that. So electric field due to a point charge. So electric field is defined as the force on unit charge. We can go further. A is F upon Q naught. Force per unit charge is called electric field. What will be its unit? Newton per coulomb. This charge needs to be very small so that the original field of this charge is not disturbed. If I take this charge very stronger than this, then this field will be repelled. We want to check the electric field at this point due to this. So this charge should be negligible. Only then the effect of this or electric field will remain close to the actual value of the field. So what we need, that this Q naught should be 0. So should be very close to 0. So we write it this. Q naught, we read it as Q naught tends to 0 limit, which means that Q naught is very small. No difference in calculation of the electric field due to this, but you have to keep in mind that the test charge needs to be very small. Okay, what will be the direction of this field? We have seen that this is the force on test charge and it is positive charge. So the electric field direction will always be the force on positive charge. So wherever you want to find out the electric field, assume that there is a positive charge and see the direction of force. For example, in this case, it is plus, I have to find field at this point. So assume that there is a positive charge. What will be the direction of force? This will, this. So this is the direction of the field. This is positive charge. What is the field at this point? If I assume positive charge, this will be repelled. So this is the direction of the field. If I take minus charge, want to find out here, assume a positive charge, this will be attracted. So this is the direction of the electric field. At any point, if I want the field direction at this point, force is always along this line. Positive, repulsive, so this is the direction of the electric field. This is how we find out the direction of electric field. And how to represent it? Representation of electric field. Graphically, that in any region, suppose in this, on this paper there is an electric field. So we have also made a provision to represent the electric field graphically by drawing lines. We call them lines of forces. It's a curve actually. Though maybe a straight line too. It's a curve in general which is drawn in such a way that tangent to this curve at any point gives the direction of electric field. Electric field lines or lines of forces are the curves drawn in such a way that the tangent at any point gives the direction of the electric field. These are the imaginary lines actually. They don't exist in reality. There are no lines actually. It's just our way to represent an electric field. So lines, and how do we draw them? It is actually a curve along which a positive charge moves if it is free to move. So I take a positive charge here, okay, and ask you draw the field lines. So assume that there is a positive charge here. What will be the direction in which it will move? This. If I take a positive charge, this. If I take a positive charge here, see, keep the positive charge close to it and see the direction in which that charge moves. This gives us, these are the field lines. For a minus charge, it will be towards it. Away from positive charge and towards the negative charge. For any electric field line, if I take a field line like this, so it means if a positive charge is here, it will be moving like this. It also means that direction of field at this point is this. Direction of field at this point, this. Direction of field is actually given by the tangent. And direction of field is also same as the direction of force on positive charge. Okay, now just imagine if it is possible or not. Just think whether this is possible or not. I have given you two lines of forces, and at this point, see, one tangent is this, one tangent is this, which means at one point there are two tangents. It is possible or not? Just think yourself. We can, okay, then if I give you the lines of forces like this, we have lines which are parallel and also equidistant. It will always mean uniform field, constant in magnitude and constant in direction. Okay, if the electric field lines are like this, I gave you 2 points A and B. Is the field at A same as at B? No. Density of these lines will tell the relative magnitude. So here the lines are very close. Here the lines are moving apart. So field at A is higher than at B. Parallel and equidistant lines, uniform field. Lines diverging, field is decreasing. If lines are converging, the field is increasing. You may do some more examples for electric lines of forces. You may draw them for plus charges separated by some distance. Then you may do even for plus and minus charges kept very close to each other. Try them yourself. Thank you.